Good morning, everybody. Welcome back. So, recall in the last video, we derived an expression for the delta over dx. However, we don't know what is the shear stress. In this case, is tau w. So, I give you on two equations we can use to find in the textbook to find the expression. So you have 8.13 or you have 5.60. But in this case, we use 8.13, okay? So let's say what 8.13 say. So let me write. Equation 8.13. So you say tau W equal to mu, which is viscosity, times the partial of Vx over V over y at y equals 0. Okay, so that is our tau w. Let's evaluate this term right here, the partial Vx which is with respect to y at y equals 0. Let's say what does it equal to. Okay, you recall that Vx over Vx infinity, right, equal to 2 times y over delta minus y squared over delta squared. Okay, that is the given velocity profile. This is what you're gonna do. You're gonna times Vx infinity both sides, so you get Vx equal to 2 Vx infinity over delta times y minus Vx infinity over delta squared times y squared. Okay. Okay. And then you're gonna take the partial with respect to y both sides. So Vx equal to partial y with respect to y up 2 times Vx infinity over delta times y minus Vx infinity over delta squared times y squared. So you get partial Vx with respect to y equal to, treat this like taking derivative. So you get 2 times Vx infinity over delta minus Vx infinity over delta squared times 2y. Again, y, this term right here is a constant. Vx infinity over delta squared and 2 times Vx over delta is a constant. So you treat them as a constant. Okay, so what is Vx, partial Vx with respect to y at y equals 0? It equal to 2 times Vx infinity over delta minus Vx infinity over delta squared times 2 times 0. You substitute 0 in y, and so you get 2 times Vx infinity over delta. Okay, so that is your partial. You substitute this into your tau w. So I write substitute into tau w. So you get tau w equal mu times 2 times Vx infinity over delta. Okay, so go back to our equation. What will we arrive at? We arrive at okay, this is our equation above. 2 over 15 Vx infinity squared over d delta over dx equal to tau w over rho. So I will substitute tau w in, so you get, let me write, back to original equation, you will get 2 over 15 times Vx infinity squared times d delta over dx equal to tau w over rho, which is mu times 2 times Vx infinity over mu times rho. Okay, so let's clean it up and make it look nice so we can proceed to the next step. So what I'm gonna do is I'm gonna times Vx infinity over 2 on both sides. So I'm gonna time 1 over 2 times Vx infinity times 2 over 15 times Vx infinity squared times d delta over dx equal to 1 over 2 times Vx infinity times mu times 2 times Vx infinity over delta times rho. Or you can say cancellation, both work, okay? I'm just doing it so it makes it look nice in the notes, and you can use it on the exam as well, so that it's hard to take off point from you. Okay, so let's say what cancel out. 2 cancel out right here. Vx infinity become Vx infinity. On the right hand side, 2 cancel out, Vx infinity cancel out, so you get Vx infinity over 15 times d delta over dx equal to mu over delta times rho. Okay, I'm gonna do something called a program game remove. I'm gonna make sure, this is very important, I will ensure that delta and everything related to delta is on one side. So this is a method you can solve differential equation. It's called separation of variable. Separation of variable. Okay, so how do we do that? I'm going to times delta, first of time dx both sides, so Vx infinity over 15 times d delta equal to mu over delta times rho times dx. Okay, and then I'm going to times delta both sides, so Vx infinity over 15 times delta times d delta equal to mu over rho times dx. Okay, now to make it even look nicer, I'm going to times 15 over Vx infinity both sides. So this becomes delta times d delta equal to 15 mu over Vx infinity times rho dx. Okay, so now you have everything related to delta and d delta on both sides. Right here. Perfect. So to the last step, we can solve for delta using separation of variables. So let me write. Step 3. Solve for delta using separation of variable. Okay, so how do we do that? We have separate already, so now we're gonna integrate from 0 to delta. Okay, remember that delta vary from 0 to delta, and similarly Vx infinity times rho, x vary from 0 to x dx. Okay, so what is this equal to? This equal to delta square over 2 minus 0 square over 2 equal to 15 mu over Vx infinity times rho times x minus 0, right? So now you get delta square over 2 equal to 15 mu x over Vx infinity times rho. I'm gonna times 2 both sides, so you get delta square over just delta square. Delta square equal to 30 mu x over Vx infinity times rho. I'm gonna divide by x squared on both sides, so I get delta square over x squared equal to 30 mu over x times Vx infinity times rho. Okay, so look at this term right here on the right. This term right here on the right, I'm gonna do some transformation. I'm gonna divide by mu on the denominator and numerator, so I get 30 over rho times Vx infinity times x over mu. And is this term familiar to y'all? Please pause the video and ponder this amazing beauty right here. Rho times Vx infinity times x over mu. Is this something very familiar? Is it something look like rho times u times d over mu? Exactly, that is the Reynolds number with respect to x. So I write equal to 30 over Rex. And then if you take the square root both sides, you get delta over x equal to square root of 30 over square root of Rx equal to square root of 30 is approximately 1.38, and Reynolds number square, you can write it Reynolds number to the power 1/2. Okay, and ladies and gentlemen, this is our dimensionless velocity profile, delta over x as a function of the Reynolds number. In the next video, we will continue the saga and see what the problem asks us to do. Thank you everyone for your attention.